Okay, this is part 2. This is part 2 of simplifying radicals, so 9.1. We'll call this part 2 of 6. And this one specifically is new. You guys haven't seen this before. And this is called rationalizing the denominator. Now, rationalizing means make it so there is no square root, specifically in this case in the denominator. In the denominator. So rationalizing the denominator. So there's a rule, a guideline, that says no square roots are allowed in the denominator. I keep spelling denominator wrong. Okay, denominator. Okay, denominator. Okay, quick little side reminder. So let's put a little side reminder of what you were allowed to do in the past. Say you had 2/3. Could you change this so the denominator had a different number? For example, if I chose to multiply the denominator by 5, do you remember what I also would have had to do? I'd also have to multiply the numerator by 5, which in this case would be 10 over 15. This is what we used to do sometimes to find common denominators. And the reason we're allowed to do that is the 5 over the 5, technically, is 1. So you're really just multiplying by a unique version of 1. So this was allowed. This is from middle school. When you're finding a common denominator. Okay, so what we're going to have, so example 1, what we're going to have is we're going to have 5 in the numerator and another number in the denominator. So this time there's a square root in the denominator. We didn't have this on part 1 of 6. We only had this. We only had perfect squares in the denominator in that part. So we have this situation. And we're not supposed to have the square root in the denominator. And you can't just square the top and square the bottom. That's illegal. So that's impossible. It's a possible idea, but it doesn't work. So someone came up with this, and it's really important to use a different color for this one. What someone came up with is that I can multiply the numerator and the denominator by the same thing, just like I did in the yellow on the right side. But what should I multiply? So what they decided, and I'll show you how it works out so nicely, is they decided to multiply by the square root of exactly what's still inside. So if still inside is a radical 3, then you're going to multiply by a radical 3. Because what that gets you is that's going to get you 2 radical 3s. And that'll allow you to free it because you need a partner. So the 3 needs a partner. Let's multiply by another radical 3. It'll become radical 9. I'll show you how it works in the denominator. And then we have to worry about the numerator in a minute. So let's not worry about that right now. But this is the plan. We get the square root of 9. You are allowed to multiply what's underneath the radicals. And then the square root of 9, we get back to having those 2 matching 3s. And your answer is plain 3. So this is the magic. But how can we legally do that in math? So if you multiply the denominator by radical 3, just like over here in the in the yellow right here, where I just highlighted in blue, you have to multiply the same thing on the top and the bottom. So that's why I like to do it in another color, so I can really see that I remembered to multiply the numerator and the denominator. So what legally allows us to do that is this radical 3 over radical 3 is really 1. But it's a very useful one. Now, when you're multiplying radicals, the way that it works is if you have an outside and an inside, I'm writing over to the right, and you multiply it by an outside and an inside, you're allowed to multiply the out times the out, and you're allowed to multiply the inside times the inside. So this specific 5 is an out, and the 3 is an in. So you can't multiply the 5 and the 3 and get square root of 15, but what you do is you multiply and you get 5, and then you keep your square root of 3, because one's inside jail, one's outside jail. And then 5 radical 3 just comes over to the side. Check if these two front numbers have anything in common. They're both outside, so they're eligible to reduce, but they don't reduce. There's no number that goes into 5 and 3. So that's it. And that's the answer for this one. So what's new is we are multiplying by the square root. So let's write this in words. We're going to multiply by the square root that is in the denominator. Let's take a look at another one. This one's going to be a little bit different. Okay, this one is the square root of 12 over 5. Now it looks a lot different from example number 1, but it is a fraction, but it's a little different. So we're going to do what we did on the previous video, which is, what do you think? What do you think? What did we do? And what did we do when it looked like this? Square root of 4/9. What did we do? We square rooted the 4, and we square rooted the 9, which would have been 2/3. So this is old. So what do we do on this one, the one that we're working on? So square root the 12 and square root the 5. Now for me, any time I see a number that makes a tree, I know that the numbers get friendlier if I make the tree now instead of wait till later. So if I want small numbers, I'm better off doing the tree right now. So the tree for 12 would be 4 times 3, 2, 2, 3, so 2 radical 3. 2 comes out, 3 stays in. Still have a radical 5 in the denominator. I'm going to erase this part over here so I have some more space. Hopefully you didn't run out of space. Now, I'm not supposed to have a square root in the denominator. So no radicals in the denominator. So that's not allowed. So what I do is I use the method that I just said here in blue. It says multiply by the square root that is in the denominator. So I'm going to change to red. So I'm going to multiply by the square root of what's in the denominator. If there's a number in the front of the square root, you don't have to multiply by that. You just need to get a twin. You need to get a partner for the 5. Okay, so this one becomes square root inside, inside. These are both in. The 5s are in. I get a square root of 25. And square root of 25 is 5, plain 5. So you don't need a square root. Now when I'm multiplying this square root, the numerators, I'm going to use my out, out, and in rule. But there's nothing outside the radical 5. So what do we do if there's nothing outside? See if you can remember. Remember there's a 1. Okay, so outside times outside is 2 times 1, that's 2. Inside times inside is radical. Radical what? Radical 15. Now you should make a tree for 15. That's 5 times 3. But no one comes out. So you write 2 radical 15 over 5. Now these don't cancel. So let's put a little arrow. Let's put a message. don't cancel. That's because 1 is inside and 1 is outside. So if something's inside and something's outside, then they don't cancel. In this video, we have 5 examples. Okay, so let's do another one. Square root of 3 over 7. So try to think of what you would do. Kind of looks like the one above. Separated into 2 square roots. Tree, no. Tree, no. So try to think of what you need to multiply by. So I'm not supposed to have the square root in the denominator. So this is not allowed. So I have to multiply by a square root, a matching square root. The top and the bottom have to have the same square root. That's why it's nice to have another color. But square roots in the numerator is okay. So we'll put okay on that one. So radical 3 is okay. It's the radical 7 that's the problem. So I have 1 7, and I'm trying to do square root. So I get another 7 so that I can get a twin. Later on, if you have a cube root in the corner, you need a group of 3. So that's going to be a little more complicated. But that'll be interesting. That'll be in one of the last videos of this section. So radical 7. Where are they? The 3 is inside or outside. The 7 is inside or outside. If they're both inside or they're both outside, then you are allowed to multiply them. So radical 21, square root of 49. Square root of 49, well, that just came from 7 times 7, right? So that would be plain 7. You'll notice in geometry, people skip directly. So I'll write this step in blue. They skip directly from this step to this step. I like you to put the 49 in the middle because then it makes more sense of how you're getting 7 and what the plan is. So you multiply by a matching one to get rid of the square root. And then the 21, tree, 7 and 3, nobody comes out, square root of 21. And then 21 and 7 have something in common, but this one is inside, this one's outside, so they don't reduce. That's your answer. So this is called multiplying by the square root of the bottom, or it's also called rationalizing the denominator. We talked about how rational numbers can't have an unsimplified square root. So 2 radical 3, that was irrational. We said square root of 12 was irrational. We said square root of 25 is not irrational because we know the answer is 5. So that's considered rational. So that's our plan. Okay, so example number 4, 3 over radical 6. Now this one's already split apart. Try to make a tree, 3 and 2, but nobody comes out. So I'm going to go right for the problem. I'm not supposed to have a radical in the denominator. Multiply by which radical? Radical 3, radical 6. So I multiply by radical 6. I'm allowed to do that because that's a 1. So this is 3 radical 6. This is an outside. This is an inside. So you can't really do anything. So maybe you could put a 1 here if you wanted. 3 times 1. And then this is radical 36. Radical 36 is a plain number. It's rational. So now it's rational. So the square root of 36 is 6. So now the denominator is rational. 3 square root of 6. Do these have any numbers in common? They do. What number can we divide them by? Divided by, divided by 3, divided by 3. Right? So it reduces. So that is 1 radical 6 divided by 2. This is an answer that's correct. And then another answer that would be correct would be you don't have to put the 1 in the front. So this would also be correct. But both would be correct and would give you full credit. Okay, our last example for this video is more complicated. It looks more complicated because the numbers are bigger. So I'm going to show you a way that'll make it a lot more straightforward than the complicated way. So I'm going to show you 2 different ways on this one. The first thing that we do in both ways is you square root the top, square root the bottom. It's like distributing the square root to the numerator and the denominator. Now this is where you have kind of 2 paths. One is you don't make a tree first. It's totally allowed, but your numbers get a little out of control. So if you want, you can multiply by the square root of the 48. And a lot of people do this. If they don't notice, they can make a tree first. The only problem with this method is the numbers get really big. So 5 times 48. This we could use the shortcut because basically that's going to be the square root of 2 48ths, which means they come out. So that's kind of nice to know. So square root of 5 times 48 over 48. But now you're going to have to make a tree for 5 times 48. Or if you multiply those, you get 240. 48 times 5, 0, 4, 240. Okay, so 240 over 48. And you see that that's not necessarily a number that you really want to deal with, but it just came from 5 times 48, so you could simplify it from there. And then I could keep making a tree. Maybe I should write this so we can see it. So let me do our tree for 240 over here. So 240, 5 times 48, or any other pair. If you want to multiply 10 times 24, that would work too. Then you make the tree for this one, 48. 48 is 4 times 12, maybe 6 times 8. Bring the 5 down so I don't forget it later. I like to bring them down. That's what, 4 times 3, 2 times 2. I like to bring the singletons down so that I have a whole row of everybody in the same row so I don't lose anyone. I take all the things out, take out the 2, take out the 2, leave the 5 and the 3 inside. So this would be 2 outside, 2 outside. Oops, that's in the numerator. Yeah, so square root of 15, because I multiplied the 3 and the 5, over 48. 4 radical 15 over 48. There is something you can go into. Divide them both by 4. Radical 15 over 12. Probably the right answer, but we should work it out the other way and see if we get the same answer. Now that one, the numbers get kind of big, which is okay. But if you did the tree from the beginning, so if you notice to do the tree from the beginning, so 4 times 12, 2, 2, 2, 6, 3, 2, bring down the 2, bring down the 2, bring down the 2. To make a tree. Who comes out? Circle the ones that come out, the pairs. 2 comes out. Here's another pair of 2, it comes out. 2 times 2, the twins come out, 2 pairs of twins. Radical, who's left inside? 3, 4 radical 3. So you get radical 5 over, let me change colors to black here. So this would be radical 5 over 4 radical 3. Now the beautiful thing about this one is when you multiply by the radical, you don't have to multiply by this 4. The 4 is not a problem. The only thing I don't like is the radical 3. The 4 is okay. Now in a later section, if we had a plus in between the 4 and the radical 3, that's a whole different story. But if they're right attached to each other in their multiplication, then you don't have to multiply by 4 square root 3. You can just multiply by the square root of 3. Although if you multiplied by this 4 square root of 3, it would also give you the right answer. There's many different ways to do this problem correctly. Square root of 3, square root of 3. So let's see what we get. We get square root of 15 over 4 square root of 9. Square root of 9 is plane 3. Square root of 15 over 12. And we never got the number 240. It's completely up to you. You can see which one you like better. It is also allowed to multiply by a 4 here, but then it's more work. So I don't recommend it, but if you did that by mistake, you would get still the same answer. So that's perfectly okay to do that as well. Let me erase that because usually that's not the best plan. So we might as well do a better plan. Okay, and this is going to be for the next section of problems. So it's going to start with 15. Okay, so this is the examples for rationalizing the denominators. Rationalize the denominators, and this starts at number 15 and is in the section entitled Rationalize the Denominator.